lab, and I'm working with my graduate student, Leroy Gia, who's a student of applied mathematics, and also my colleague, Bob Pelkovitz in physics. And I'll begin very quickly by telling you the particular problem that motivates us, and then I'll fill in a lot of details to give some background. So we're looking at a kind of shape instability of colloidal membranes. This is you see a scale bar here. This is a 2-micron scale bar. So this is a membrane which is made out of viruses. The constituent particles are viruses. And the particular phenomenon is when they are cooled, they go from a state where they're circular, flat membranes, and they're very soft objects. They're fluctuating. Their edges fluctuate. And the edges start to twist and turn into these helicoidal shapes. So this is the general problem that motivates us. And so here you see the outline of the talk. I'll begin by giving you much more details about these colloidal membranes, what they're made of, and how they work. I'll describe our effective theory. We're not going to try to understand all the details or include all the degrees of freedom of these membranes. And then we'll apply it to this instability and also to trying to understand the nature of the fluctuations of the edge. And all this work was funded by the National Science Foundation, in particular the Brandeis Materials Research Science and Engineering Center and the Mechanics of Materials Division of NSF. So the take-home message of the talk is shown here. So I'm going to argue that these shapes that we see, which are typically negative Gaussian curvature like a saddle, are driven by entropy. That entropy is going to favor this. So in these systems, the membrane is made out of virus particles. They're rods. We can think of them as hard rods. And there are also a lot of depletant polymers, lots of little polymers in solution. And it's the entropy of these polymers that controls everything, because there's far more of these polymers than there are of these rods. And the membrane is going to take a shape to allow the greatest volume for the polymers to move around it, to maximize their entropy. And we're going to make a simple geometrical argument that says that the saddle shapes are favored. We'll see that chirality, the intrinsic handedness of these virus particles, is also important, and that will also favor saddle shapes, and that will come into play as well. So to put the problem into a little bit of a mathematical context, I want to mention these kind of classic problems of shape optimization. So we're all familiar with the plateau problem, the soap film problem. If you have rigid boundaries like some wire loops, and you ask what is the shape that a soap film takes, it will be a shape that minimizes the area. And there are many different variants of this problem. There's a nice variant where Giomi and Mahadevan and others have considered the possibility where the wire boundaries are flexible. So not only do you have to solve for the shape of the surface, but you also have to account for the bending of the boundary and solve for that as well. So they call that the Euler plateau, Euler for the bending of the rods which are making up the boundary. Another example of this kind of mathematical optimization problem is the so-called Willmore problem, where instead of minimizing the area, you have some measure of the bending of the surface, and you, let's say with, again, rigid boundaries like two loops, you could ask what is the shape that will minimize some measure of the curvature energy. So you integrate the curvature, or the curvature squared over the surface, and that's been studied by several mathematicians. This colloidal membrane problem, we'll see, fits into this picture as we could call it an Euler-Willmore problem, in the sense that the curvature, as I'll describe, is very important for these membranes, but the boundaries are also free, and the boundaries have some resistance to bending, a little bit like in the Euler plateau problem. So we have to account for that as well. All right, so let me turn directly to these colloidal membranes. I mentioned that these are made out of hard rod particles. So the virus, here's a virus which is shown here, FD virus. It's long and thin. It fluctuates a little bit. It's not perfectly rigid, but we're going to completely disregard that fact in this talk. They're about a micron long. They're very skinny. And what Zvonimir does is he makes membranes by putting these polymers, or putting these viruses in solution with the polymers. So the dextran polymers are what I call the depletants. There are many, many, many of these depletant dextran polymers. And that picture that I drew there is sort of more or less roughly to scale. So we're going to think of these polymers as small hard spheres of a fixed radius. And under certain conditions, they make these large membranes, which are a little bit reminiscent of lipid bilayer membranes, the membranes that make up our cells. And this is one reason why people are interested in these colloidal membranes. They self-assemble. Of course, they're different. These colloidal membranes are one rod thick. They're not bilayers like lipid bilayer membranes. They're not made out of these amphiphilic molecules. They're much simpler. And also, these colloidal membranes typically seem to have edges, which is unusual in lipid bilayer membranes. So there's some differences and some similarities. The main experimental difference is that these colloidal membranes are just much easier to study experimentally. They're much bigger. The constituent particles are much bigger. Things happen more slowly, and it's just easier to study them experimentally. So I think we have a diverse audience, so I'm going to just go over some very basic things. So as I implied, these rods are held together by this so-called depleting force. So there's this beautiful short paper by Asakura and Usawa that if you haven't looked at, I encourage you to look at, where the idea is just imagine you only have two of these rods, these two dark rods. And we're going to consider everything to be hard. So the rods are hard and the spheres are hard. And there's an excluded volume or depletion zone, this light blue region, where the centers of these polymers can't get into that blue region because we're thinking of these particles as hard particles. And you can see if these two rods move around, as long as those depletion zones don't overlap, the volume accessible to the polymers is the same. However, if the rods get close enough, those depletion zones overlap, and there's more white space in that picture. There's more volume for the polymers to move around it. So that's the basic idea of the depletion force. There's an entropic force which is tending to push these rods together. You can think of it like the osmotic pressure if you'd like acting. You can actually calculate things quantitatively that way. So here is a kind of phase diagram up here on the right. So this is the concentration of FD viruses on the horizontal axis, and on the vertical axis is the concentration of the dextran polymers. And you can see that there's a narrow band where there are these unbound membranes. You can tune the interaction between the particles by changing the concentration. If you add more polymers, that's going to tend to push the membranes closer together. So as you move vertically, for example, the membranes will start to stick together. And if you have too high of a concentration, eventually you'll get other phases, liquid crystalline phases, like a layered phase. So here, the rods, they start off and they form little discs, but the discs will stack up and form filaments. That's a smectic, the smectic filament, where we have these layers. So we're just going to be working in this region where they make these nice, large membranes. Again, this is a 2-micron scale bar in that figure. These membranes are fluid. So again, a nice thing about the colloidal membranes is that you can, you can look at microscopic, so to speak, that is microscopic at the level of the single particles, the viruses, and macroscopic properties at the same time because they're so much bigger. Let's try that again. So just a few of those rods have been fluorescently labeled, and they diffuse. They just do ordinary diffusion. So the membrane is fluid. So here's the mean square displacement as a function of time. So it's definitely a fluid membrane. But there's also an interesting structure to these membranes. They're made out of the rods. The rods are all parallel in the middle of the membrane, and they remain parallel as you move out towards the edge. But at the edge, they twist. They start to twist. So that's shown here in this image. It's a kind of light polarizing light microscopy. There's been a lot of processing that's been done to this image to make this. It's this so-called liquid crystal polarizing light microscopy. Basically, it's sensitive to the birefringence, whether or not the rods are tilted relative to the vertical direction. And what you see is, what this is showing you is that the rods are tilted all around the edge. So there's a kind of penetration of the twist into the membrane. The twist can't penetrate all the way in because then it wouldn't, it'd have to tear or something. But it can penetrate around the edge. And this twist penetration depth, which we'll call lambda in this talk, is typically around 1/2 micron. Even for bigger, it doesn't depend on the size of the membranes. So what we would like to do now is start to make a theory for understanding the shapes that these membranes take. And in principle, what we should do is we should keep track of the orientation of all of these rods and also of the possible out-of-plane deformation of the shape. And many people have done that. It's a difficult problem. Actually, I don't think anyone's really put all of those elements together. What people typically do is they either fix the shape, for example, take some like a minimal surface or something, and then solve for the direction of those rods for that given shape. Or look at simpler shapes like a flat shape, like a flat membrane, and then take into detailed account what the rods are doing. Those are all useful approaches. What we are going to do is to try to make a simple theory that only depends on the geometric properties of the surface. And so things like the curvature of the surface and the curvature of the edge, for example. And the motivation is that this is the kind of thing that should work for a large membrane when that twist penetration depth is small compared to the size of the membrane. So there's all this so-called liquid crystal order, or all the interesting liquid crystal physics is taking place at the edge, but that's in a very confined region. And maybe we can summarize that by just some effective quantities having to do with the edge. So let's think about the edge. So why are the rods twisted? That's maybe the first question to think about. And the simple picture is to think of the membrane now. It is a three-dimensional object. So here's a transmission electron micrograph viewed from the side showing the rounded edge of the membrane. And this blue line is supposed to be the depletion zone, right? Where those polymers they're excluded from that zone. So since the polymers can't get in there, there's a free energy cost to having the interface between the membrane and the surface. The bigger that is, the less volume there is for the polymers. And therefore, we can say that there's something like an interfacial energy. And just like droplets don't like to have sharp corners. There's more to this than being a droplet. The rods in the middle have a certain height. They don't like to change their height. But this depletion argument is going to lead to desire for the edges to be round. And how can they be round? Well, they can be round by the rods twisting. It turns out that these rods are typically chiral. They have a handedness. They're not the same as their mirror image. But at high temperature, you can make these rods achiral. So the handedness of the rods depends on the temperature. So quantitatively, what that means is that if you make a phase which is only the rods, so none of these depletant molecules, and you concentrate them enough, you get a liquid crystal phase. You get a cholesteric phase. So in a cholesteric phase, this is actually not a good picture of a cholesteric, but it gets the idea across. You imagine the rods, it's a fluid, okay, and then as you move, let's say, in this direction, in the cholesteric phase, the rods will twist. They tend to tilt. So as you change the temperature, so high temperature, it's just a nematic phase. All the rods are pointing in the same direction. It's around 60 degrees Celsius in the FD virus. And then as you decrease the temperature a little bit below 60, there's going to be a little bit of twist, a little bit more. Even in the achiral phase, the membranes that form, first of all, the membranes form and the rods still twist at the edge. So the chirality is not necessary for the twist. The chirality, of course, will tend to make the rods all twist the same way. If the chirality is, if it's just one kind of molecule and they're all the same chirality. And then we can make the observation that because we can change the chirality, and this is the observation of Zondervan-Dojic's group, because they can change the chirality can act like a surfactant for the edge. It can change the effective line tension for the edge. So the idea is that the rods are twisted at the edge here because the entropic terms want to make the edge rounded. But then there's this alternate energy. There's some desire for the energy to twist. So N here is the direction or the director. It's just aligned with the rod. So there's some desire for the rods to twist. Q naught is the rate of twisting. So if you go from Q naught being 0 to Q naught being positive or negative, doesn't matter, one or the other, just being non-zero, then the rods are getting happier and happier as you make them more chiral, because they're already twisted and they're getting, as you change the temperature, you're getting them, that twist which is set in there is getting closer and closer to the desired twist. So by making a kind of simple liquid crystal theory, K here is some elastic modulus which for twist has been measured in this system with only rods, and knowing and measuring the twist and knowing the twist penetration depth, you can come up with a kind of effective line tension where this twist will reduce the bare line tension by some amount, which is determined by the amount of handedness.
Why is this temperature dependent?
So I don't really know the answer to that question. It's a difficult question. So in a this is something which is generically true in a cholesteric. So why? So first of all, why do they twist? So let's start there. So the molecules are chiral. So if you take two screws and put them together, they'll twist, right? So that a cholesteric molecule does not look like a screw. If you looked at it, you wouldn't. Maybe if you're an organic chemist, but me, I look at it, it doesn't jump out at me as something which is obviously handedness. So the twist is more subtle in these cholesteric molecules. And you have to remember that they're going to be spinning around, right? They're going to be these thermal motions. So you could imagine that if they're all spinning around and not correlated, that even though that it's chiral, that there wouldn't be any twist.
It averages out.
Yes, but the details of why the pitch in a cholesteric is typically a micron, and that's something that I don't really know the answer to. And I think it's something which is still under, people don't really know completely. More questions? Okay, so I just made an argument for a flat membrane that we have some effective line tension. So that's going to be one of the ingredients of our theory. Another ingredient is like this Euler plateau problem. The edge has a resistance to bending. So again, we can think of this from this liquid crystal point of view. The rods have a desire to be aligned, and you can write down some liquid, this is just an estimate, you can write down some energy cost for when the rods are not aligned. In particular, if you think of the edge where they're twisted, they're all, if it's a straight edge like this, the rods are all pointing in the same direction. So then if the edge bends, you can see that there's going to be some bending energy cost, and we could compute that, or rather estimate that from a liquid crystal theory. This elastic constant K3 has not been measured for these rods, but often in liquid crystals people assume that they're all of the same magnitude. So if we assume that this K3 is the same magnitude as the twist constant, which has been measured, and we know what this twist penetration depth is, then we know the area over which the director will vary. We'll be able to estimate the gradient. We know D here is the thickness of the membrane. We can come up with an effective bending energy of the edge. We'll treat the edge just like an elastic rod with some bending energy, and putting all these things together, we come up with a bending energy which is about 100 kVt microns. That's what we expect the bending energy of the edge to be. Okay, so I have these two ingredients and we can put them together. We've got an energy now for a flat membrane. I'm not allowing it to bend out of the plane yet. I've got the line tension gamma, the bending energy, K is the curvature of the edge, it's in the plane. And these, as I said, these are soft objects, so the edges fluctuate. So these are some images from Zvonimir's lab. These are just snapshots at different times of the edge of a large membrane. This is a 5 micron scale bar. And they measure the fluctuations. They measure the power spectrum of the fluctuations. They look at the amplitude and they average over time as a function of the wave number q. And we can, because the fluctuations are not so big, we can use the equipartition theorem to say what the amplitude should be. If u is the displacement of the edge in the plane, then we can approximate the line tension. If there's any gradient in u, that's going to lengthen the line edge length. And the bending stiffness has to do with second derivatives of the displacement of the edge. And they chose to plot not the mean square amplitude of the displacement, but they multiplied it by q squared. So this is what you would expect from this simple theory, that it should go like gamma plus e q squared. So for For large Q, the bending should dominate, right? Because that's where it's going to be, there's going to be a large energy cost for something which is really wrinkled up, or an edge which is really wrinkled up, and this falls off, this is a log scale, this falls off like 1 over Q squared, and the slope of so it gives it the slope is 2, but the number that you get for the coefficient here is about 100 kBt microns, so it's consistent with our estimate on the previous slide. For small q, the fluctuations are going to be governed by the line tension, and these different curves are for different temperatures. So the top one is low temperature, 5 degrees, 20, 60. Remember, 60 is where the chirality starts to, where it goes away. What we are seeing is that at low temperature, the fluctuations are bigger. That's consistent, again, with our argument that at low temperature, the chirality is bigger, the line tension should be bigger, so the line tension will be less effective in reducing the fluctuations. So that all sort of fits together. So we'll come back to the edge later on, but that's our basic ingredients for the energy of the edge.
Shouldn't there be spontaneous curvature at the edge?
There does not seem to be any spontaneous curvature of the edge, in the sense that we've looked at these fluctuation spectrums carefully and haven't, you can put in the spontaneous curvature.
I mean, you would expect one in the sense that obviously the inward side of the edge and the
Yeah, they're different,
side
sure.
are
It's
totally
different than the
so-
outward side. That's
so
true.
It's odd that there's nothing there.
It's odd it could just be so small that, it's true, it's not symmetric.
Because the other thing is, which is difficult to understand, is why these things have a particular size, rather than just aggregating. I mean, if you have something which just has a free energy per unit area and a line tension,
Yeah,
thermodynamically you expect it to be infinite sheets. You don't expect it to be finite disks. And it might, spontaneous
Spontaneous
curvature
curvature.
at the edge was one of the few things I could think of.
yeah, sure, would give you a
might
light
rescue
scale
that.
that could do that. Could be. Good to consider, yes. All right, so let's think about the surface deformations. So we're going to use the Helfrich theory, which people have used for membranes, and actually the question leads us right into this in a sense. So we're going to, okay, first I have to say that this is a theory which is going to treat the membrane as a two-dimensional surface, very, very thin. It's actually not all that thin. Remember I said that the thickness is about a micron, size 10, it's true that the size is not fixed. There can be big membranes and little membranes, but they're not enormously large compared to their thickness. We're just going to set that aside and see how far we can get by using this Helfrich model. So there's a cost for bending. So h is the mean curvature. At each point, we have two principal curvatures. Their average is h. And kappa, with units of energy, is a bending stiffness for, it's a modulus, bending modulus for these membranes. The top and the bottom of the membrane is water, and the rods themselves are symmetric, so we don't expect any desire to curve one way or the other. So we don't have a spontaneous curvature for the bending of the membrane. The second term in the Helfrich energy is this Gaussian curvature term. So K here is the product of these principal curvatures. And when people study lipid bilayer vesicles, they typically don't worry too much about this term because this term doesn't depend on the shape. As I say, it doesn't depend on the geometry of the shape. It integrates to a topological invariant. But if the membrane has edges like our edges, then the integral of the Gaussian curvature does depend on the geometry. It turns out that it can be written as an integral over the edge of what's called the geodesic curvature. The geodesic curvature is the curvature of the edge in if you look at the edge in the tangent plane of the edge. So for example, if you look at a great circle, the equator of a sphere, that has zero geodesic curvature, because if you're walking along a great circle, you wouldn't measure any curvature of the Earth, right? It's all bending into the Earth, it's not bending in the plane that you're walking in. If you imagine shrinking that circle to a little circle around the North Pole, then you would have a curve which is curved in the plane of the surface. That's all geodesic curvature. Okay, so that's something that we know how to compute. I'm going to make an estimate for what kappa bar is. Kappa should be easy to estimate, but right now in this area, we're a little bit confused about the magnitude of kappa. Kappa has been measured experimentally by looking at the membrane's edge on and trying to focus on a line, say in the middle of the membrane where the membrane itself is fluctuating, that is to say not the edge. And by doing a calculation with this energy, using the equipartition theorem again, you can come up with a value for kappa that comes out to be 150 kBt. That value seems far too small compared to other things that happen in the experiments. If kappa really were 150 kBt, then these membranes should easily be able to fold up into vesicles because the line energy cost should drive that, and they don't unless the rods are very, very thin. Vonnegut thinks that perhaps his measurement of kappa was maybe there was a problem with it because perhaps in looking at the fluctuations in the middle of the membrane, he was seeing the front and the back. So that's still an open question that needs to be resolved. We do think, however, from basically the fact that these membranes don't wrap up and form vesicles, and from some other preliminary things that Vonnegut is working on, we do think that kappa is very, very large. And therefore, for the rest of this talk, I mean, we can keep kappa in and we can do all the calculations, but we're going to assume that this bending stiffness kappa is very, very much larger than kappa bar. So that's something that is still really under study. It has to be resolved. So let's look at kappa bar. Kappa bar, we want to this is just an estimate. It's not really a rigorous calculation of what kappa bar should be, but it's of the same nature of the previous estimate I made for the bending stiffness, a little bit more involved. Typically in lipid bilayer membranes, kappa bar is thought to be negative, favoring spheres, so things with positive Gaussian curvature. But we see in these colloidal membranes, they often make shapes of negative Gaussian curvature. So let's try to calculate it. So there are two contributions. There's one contribution which we could call an intrinsic contribution. So just like if you take a solid plate and you bend it a little bit, you could calculate what the Gaussian curvature modulus is. It's in Landau and Lifshitz, and for a solid plate, it turns out to be negative. There's a similar kind of argument that Helfrich put forth for a fluid membrane, which is a little bit different than the solid plate membrane because it's not a solid. The physics is a little bit different, but it relies upon the same geometry, which is that when you bend the surface, the strain in the surface as a function of the distance z from the middle of the surface is going to depend on the curvature. So we can agree that if you take if I take this and I bend it, I don't want to bend it, I don't want to break it, the outside is going to be longer than the inside. So that's this first term. But if we go to second order in the displacement, it turns out that there's a contribution of fixed sign, right? The first order term, it's longer on the outside or more area on the outside, less area on the inside when you bend it. But if the Gaussian curvature is positive, then the area goes up a little bit relative to the first term for both the inside and out. So putting all this together, Helfrich made an argument that the Gaussian curvature modulus is given by the second moment of the in-plane stresses when the membrane is not bent. And we can say, well, these polymers are going to squeeze these rods together, so there's some lateral in-plane stresses, some compression when the membrane is not bent, and we can come up with an expression which involves the thickness of the membrane, capital D, and the diameter of the polymers, little d, and it's negative. We can come up with an estimate which is negative. So the intrinsic contribution to the Gaussian curvature modulus from Helfrich's argument, and adding some of this depletion stuff, is negative. There's another contribution which has to do with these polymers. The polymers are free to move around in space, and we have to account for their entropy as well. And we simply use Asakura and Usawa's argument for calculating the free energy. We calculate how does the accessible volume depend on the curved shape of the membrane. And again, because of this second order term here, it turns out that for a surface of negative Gaussian curvature, that the depletion zone gets smaller when compared to a flat membrane when you have negative Gaussian curvature. So there's more room for the polymers to move around in, which would lead to a positive contribution to the Gaussian curvature modulus. So that's geometry, and we can carry through the calculation and we come up with some expression that depends on the thickness of the membrane. So it depends on the thickness of the membrane because the membrane has two sides, and it's much thicker. D is a micron, much bigger than 10 nanometers or 7 nanometers, which is the diameter of it's the diameter of the rods, but it's also the diameter of the, actually they're even smaller. So we come up with an expression. And this argument, it's really the same argument that Milner and Witten made for the contribution to the Gaussian curvature modulus for a polymer brush, where if you imagine a surface, let's say it's flat and it's got some polymers attached to it, and there's some free energy cost for that system, and then you put it into a configuration with negative Gaussian curvature. What I just argued here is that the region here is where the polymers are sitting is smaller and they're squeezed together more. There's going to be a positive energy cost. So they argued that in this different system, the Gaussian curvature modulus should be negative, that there should be cost to this, so to negative Gaussian curvature. So it's the same kind of geometrical argument. So we can put these two terms together, this intrinsic and polymeric contribution, and the polymeric contribution wins. We come up with some expression for the Gaussian curvature modulus, which we estimate to be about 200 kBt. So, now, of course, we would like to check this with experiments, and we're still working on this kind of thing. We have one example, which is really due to Nadir Kaplan and his calculations, where he's looked at a slightly different system than the one I've been describing, and come up with a way to calculate what the Gaussian curvature modulus is based on the shape. I can't really do it justice here. I'll just give you the briefest of a description. So here again is one of these membranes, but now you notice it has some cuffs in it. So this is a membrane which is made not out of a single component of rods. It's made out of two different kinds of rods. It's a mixture of right and left-handed rods. So you have these FD viruses, and they do a kind of point mutation. So there's a protein that they mutate, and again, it's a subtle thing that it goes from having one-handedness to having the other-handedness when you have them alone in the bulk liquid crystal solution. But otherwise, because it's just a small mutation, the shape is pretty much the same. The rods are the same length, they're the same diameter, the same coarse shape. When they mix these rods in a membrane, so now we have a two-component membrane, they don't phase separate, and instead of seeing those smooth edges, you see these cuffs. And what you cannot tell from this picture is that these bulges sometimes, well, they actually very orderly, let's say this one goes below the plane of the screen, and this one comes above the plane of the screen. Below and above, there's always an even number, so they go up and down, up and down, there's a cusp. So in the mixture where it's achiral in the sense that if you take the same ratio of right and left-handed rods and make a liquid crystal phase out of them, there's no chirality. That's what we mean by achiral. So if we look at that mixture and make a membrane with that ratio of left and right-handed, you see that these lobes are all about the same size. And again, there's a kind of fluctuation in the length or the size of the lobes. And then as you start biasing, having more of one handedness than the other, what you see is that some of the lobes are smaller and some are bigger. And I don't have a figure of it, but again, by using this polarizing light microscopy, the experimentalist can tell what is the sense of twist in this lobe and what is the sense of twist in that lobe. It's always alternating. It's one-handedness here, the other-handedness there, back and forth. So the one which is longer is the one corresponding to the greater population of handed molecules. Okay, so it's a kind of a log-involved thing. What they do is they look at the fluctuations of the size of these lobes, and it's effectively like a kind of interaction between these cusps. And Nadir Kaplan did a calculation to see what should be the expected spring constant of the interaction. And because these lobes are coming up out of the plane, and then they have to, well, it has a saddle shape, right? If it comes up out of the plane, and then as you go back into the membrane, it goes back down, there's something with a negative Gaussian curvature. It depends on the Gaussian curvature. And from that, he's able to back out kappa bar. And it's suspiciously close to our estimate. It comes out to be like 180 kBT. So I'll just say it's in the right ballpark. Okay, so those are our ingredients. Oh, good, okay.
But your model has only one kind of rod.
But ours has only one kind of rod. So this kappa bar might be different from ours. This is the best we can do. So this is the only measurement so far. Good point. Okay, so last ingredient. I mentioned I keep talking about the chirality, but all the terms that I've written down don't have anything to do with chirality. The line tension is mirror symmetric. The bending stiffness of the edge is mirror symmetric. We've thrown out the liquid crystal order. If you include liquid crystal order, you can put in twist, but we've thrown that out. So is there any geometrical quantities that we can include that are sensitive to the handedness? And there are, but first I just have to do a quick little review of the geometry of the edge, now where the edge can go into three-dimensional space. So we remember the Furness-Sorey firm. If you've got a curve, there's a tangent vector, there's a unit tangent vector, there's a unit normal vector, which is going to point to the center of curvature, and then the binormal is the cross product. So the curvature of a curve is the rate that the tangent rotates around the binormal. Okay? And the torsion of a curve is the rate that the normal rotates about the tangent. So for a planar curve, there's no torsion. A helix, think about a helix, you've got this helical line, which I didn't draw very well, going around this green cylinder. The center of curvature is the center, the axial line running up the center of the helix. So the normal is always pointing towards that. The normal is rotating around z. And the vertical direction, z has a binormal component and a tangential component, so it's got both curvature and torsion. So that's the torsion. It's the rate that the normal, the curve rotates about the torsion. And that is a handed quantity. It depends on, its sign depends on whether the helix is right-handed or left-handed. So can we use that? Can we put an energy? Can we make an energy for the edge that depends on the torsion? And immediately we run into a little bit of a problem, which is that, well, we would like to describe edges that are straight. And what do I say the torsion is? I can say what the tangent vector is for a straight curve, but what do I do for the binormal? The normal could just sweep around, could rotate around. It's not really well defined. But for the edge, it's not just a curve. It's got some structure to it. The inside is different from the outside. And in particular, it has a normal vector. That is to say, there's the normal vector to the surface, which I called NC here. So there's another kind of torsion. There's the so-called geodesic torsion, which is the rate that this normal vector to the surface at the edge rotates around the tangent. And that's a well-defined quantity, even if the edge is straight. And it is sensitive to the handedness of the system. And we have not derived, so we can make an energy term out of this geodesic torsion. We can say that there's some spontaneous torsion, or spontaneous geodesic torsion, some desire for the edge to twist. Now, I want to emphasize, we're just being phenomenological here. I'm just trying to imagine all the possible terms that are consistent with the symmetry and and are of low order, and we're just going to say they have to be here. We haven't derived this from some liquid crystal energy, which would be nice to do. So there's again going to be some effective bending stiffness, B prime. We don't know what this is. We're just going to say it's about the same as the edge bending stiffness, because by dimensional analysis it has the same magnitude. And so there's a preferred torsion. So this preferred geodesic torsion should be proportional to the twist, the Q naught that I was talking about earlier of the molecules. So there's some cross term here, tau G times tau G star. So I'm going to call this combination B prime times tau G star C star. That's our going to be our effective parameter. So we're taking B prime to be equal to B, and now we've got this chiral term, which is only at the edge. So here's everything again. So we're taking the bending stiffness to be very, very large. So let's just make the presentation simpler. So I'm only going to consider surfaces that are minimal, have zero mean curvature. We've got the line tension of the edge, the bending stiffness of the edge times k squared, and then the same cost for having geodesic torsion. Gaussian curvature is important. And finally, there's something which will give us a preference for one handedness over the other. So what controls the rippling and stability? We're not going to solve this problem. We're going to look at a much simpler problem, which is the problem of the instability of an infinite edge. So we have a semi-infinite, a surface. So it's going off to infinity to the left, but it's got this infinite edge here. And we're going to ask, when does this energy prefer the edge to be rippled, as I've drawn there? So now I can speed up. So I can finish in the next 10 minutes. The problem is here. So again, here's the straight edge, and here's the rippled edge. So we're going to look at the edge. So okay, so what are all these things? So y is along the edge, and x is perpendicular to the edge. So the edge, the curve RC is the edge, and it can have a horizontal component, an in-plane component, and a vertical component. So U is horizontal, that's what we used before, and V is vertical. Zeta, we're looking at small deflections, so zeta is the fluctuations of the surface. It's a minimal surface, so it's a harmonic thing, so we can solve for what the height is. And now we have to figure out what the energy is. So now I've got the height in terms of the displacement of the edge, the vertical displacement of the edge, and I can stick that into the energy and get an energy that depends only on the shape of the edge. It's got some vertical components, dq, these are Fourier components, and horizontal components. So this term is what we saw before. We've got the line tension times gamma squared, the bending stiffness times q to the fourth. There's a typo on here, but that's okay. We have the same thing for the vertical components. The typo is that there should be another contribution coming from the torsional stiffness, but that's okay. We'll just give a factor of 2 somewhere in there. And when the membrane has a vertical out-of-plane deflection at the edge, you can see that, again, it has to have some Gaussian curvature, right? It's curved one way along the y direction, it's curved the other way. It actually has a saddle shape here, so the Gaussian curvature will come in, independent of the handedness. Q, the sign of Q is going to tell you the handedness. Then there's also some coupling. Because of the chirality, and this is important, there's a coupling between the horizontal and the vertical fluctuations, because the chirality would prefer the edge to have a kind of helical nature to its fluctuation. So that's important actually for doing the experiments, or rather for interpreting the experiments. So the interesting, I think, the most interesting thing is this if we could look at just the vertical fluctuations for an achiral system, there should be a peak. There should be something interesting that happens there. That could be a way to measure the Gaussian curvature modulus. And that's something which is being pursued. But right now, the experiments are not there yet. It's a very, as I mentioned, it's a very difficult measurement to look at these vertical fluctuations of the edge and be sure that you're looking at these vertical fluctuations. There's also a problem with the resolution. The scanning is not fast enough. I'd also want to mention, this was a little bit embarrassing for me. My colleague, Huajin Gao, in Pradeep Sharma, who I haven't spoken to recently, I hope he's okay in Houston, have done pretty much the same kind of calculations for the edge fluctuations of graphene and lipid bilayer membranes. They just did molecular dynamic simulations. They haven't been looking at experiments, but they've also been looking at these kinds of edge fluctuations very recently. But the point is that for us, and for an experiment, it's very difficult right now to measure these vertical fluctuations in an experiment. It's just a challenge which I hope will soon be resolved. But you can see here that, as I mentioned, at some point this is going to, the fluctuations are going to diverge. What does that mean? That means that the energy for the edge is the same. The energy for the straight edge is the same as the energy for the rippled edge. That's signal the onset of the instability. So we could make a little phase diagram if C star is on the x-axis here. So if it's achiral, we're just moving up in the vertical direction, and there's some critical value of that Gaussian curvature modulus, which will depend on the line tension. As you make the line tension gamma bigger and bigger, that's going to resist the rippling of the edge. So we have a kind of phase diagram simply, and of course, if there is some chirality, that can also drive the instability, because that the chirality is giving a preference for the edge to twist. Now, I mentioned that these vertical fluctuations are difficult to measure. The experimentalists right now can only look at the horizontal fluctuations, but our formula tells us how we can see the effects of chirality and the Gaussian curvature modulus in the horizontal fluctuations. Because remember, because the system is chiral, there's a coupling between the vertical and the horizontal fluctuations, and therefore kappa bar is going to enter. So this is, again, the power spectrum, the plot of the mean square amplitude of the fluctuations as a function of Q for different chiralities. Light blue is 50 degrees Celsius, so that's less chirality. Increasing chirality means smaller line tension, and you see this peak developing. There's a couple caveats. So there's experimental data here, and then there are our fits. We fit two things, the line tension and C star. And again, they're reasonable values. As we change the temperature, those are the two things we fit to try to get some kind of agreement. So the message is that a peak is observed in the fluctuation spectrum, and this peak corresponds to the development of these ripples. The length scale is right about the length scale that is seen where the ripples develop. This is different from the plot I showed you earlier when we were looking at the in-plane fluctuations of the edge. And this is another one of these mysteries. This is a different sample. So it turns out there are two different samples. One sample does not form those ripples, does not form the twisted ripples. That's the one I showed you earlier. We're changing the chirality, just changed the height of the amplitude over here, right? There was no peak in the first fluctuation spectrum I showed you. It's not clear what the difference is between these two samples, other than that, one expresses its chirality, other doesn't. Who knows what happens sometimes? Maybe there's a mutation or something, and the virus is not the same as what you thought it was. But anyhow, here we see this peak, and it's and again I want to emphasize that this is the in-plane fluctuations, and we can't. It's not really. It doesn't depend enough on the Gaussian curvature modulus for us to really give a sharp measurement of the Gaussian curvature modulus. All we can say is that we use a value of 150 kBT for all of these curves, and that seems reasonable. So again, the message, and I'll conclude here, is that we have tried to push a simple effective geometric theory as far as we could. It's only going to be valid when that twist penetration depth is small compared to the size of the membranes. We made an argument that for entropic reasons, the Gaussian curvature modulus should be positive, which is not unprecedented, but is somewhat unusual. And and then we made a calculation that this rippling instability we think is driven by the Gaussian curvature modulus and the chirality. there's a lot of people who've worked on this. Like I mentioned, Leroy Gia and Bob Pelkovitz. I've had some nice discussions with Randy Kamian, who also had this idea about the positive Gaussian curvature modulus from entropy. Bob Meyer, Thomas Gabod, Nadir Kaplan, I mentioned, did these calculations for the cuspy membranes, and others in working with Tranimir Kojic. So I'll stop here and take any questions.
This happens, this is not about your mathematics, but it happens only for this one particular kind of viruses? Or what, and is it important for their functioning that they...
Right, I don't think it's important biologically for their functioning. These viruses were chosen, Seth Fraden and others at Brandeis have been using these viruses for many years to study liquid crystal colloidal systems. They have various mutants that are long and short, but they're chosen because they're rods, and they're really chosen to study these colloidal systems. Because they're all genetically identical. If they're not, they can't reproduce that phase diagram, for example. So it's more of a materials application than. Maybe you could learn something about lipid bilayer membranes. These colloidal membranes, if you have two, I mentioned the ones, there was no phase separation in the example I gave, but there are other examples where they use short rods and long rods, and then they get phase separation. You get things that look like lipid rafts. And it's a different system, but maybe there could be some insight from the colloidal membranes that could be applied to lipid bilayers.
Somehow follow up on that question. So this is a great system, I think, because you can look at the edge. Is it unique to this system, or?
So you can look at the edge?
Yeah.
That's the point of view we've taken. I don't know too many other examples where you have these, it's over the course of doing an experiment, they're stable and you can really analyze it. And they're also ubiquitous. It's easy to get the edges. I don't know of another example.
Do you have a sense of what are the interactions between the viruses? Do they have electrostatic interactions or charge?
They do. I haven't studied that. So these, I didn't mention it, but these are done in a high salt situation, so that it's not that the interactions are highly screened. But so Mike Hagan looks at that. He does molecular dynamics simulations, and he worries about things like that. So, but it's the effective diameter of the rods having to do with electrostatics is still very close to the actual diameter. So for the kind of stuff we're doing, I think we're not driven to consider that.
Okay, so
But
they're
if you're doing-
self-organized because of entropy.
Yeah,
It's
I
really
think they're really hard rods.
in this system. It's really
Yeah.
Do you have a question?
I do. Go ahead. Come away.
Oh, go ahead.
You had, you've got this instability. Your fluctuation, your measurements of the power spectrum were on the stable side or on the unstable side?
Stable side.
Yeah, so
Should
what,
say that, yeah.
what can you see on the unstable side? I mean, you should get, like the edge of a piece of kelp or something, you should get a pattern of rippled edge that you should be able to characterize perhaps more precisely than this.
How do you mean?
Well, the
So-
instability is going to take you to a disk with a specific crinkly edge.
Oh,
Yeah.
okay, yeah, so if you just go a little bit.
That, I mean,
Yeah, not go all the way, but something.
Well, the
right.
bottom right picture there.
Yes, yes,
Do
yes, I
you
understand.
expect that to be the ground state at
Yes.
some point?
Yes.
Except that it's going to have helicity along the
Yes,
edge.
yes. Haven't done it either experimentally or theoretically, yes.
But in the images there, is that thing on the right really what happens?
That's
Because that's kind of rather fragmented.
that's like going far into the.
Right.
What you're saying, I think, is
So
that.
something like the third picture
Yeah, so this,
is on the unstable side.
right, right, so this,
that's not a thermal fluctuation, obviously. That's
yeah, all this So this is like, you have the stable membrane, and you make a big change in the temperature, and then it makes, right? So this is time.
Okay, so that's a deep quench.
Right, yeah, deep quench, right, so,
Okay.
yeah, they don't, yes, we would like to see that. Haven't analyzed that, yes.
And then the only other thing, there was an expression, well, maybe, is it one more? Maybe the next one. Yeah, so K bar, now you've reduced this just to the coordinates of the edge.
Right.
So the K bar Q cubed term, to get that, are you doing some integral over the saddle shape
Yes.
or can you get that actually from the topological, from the kind of Gauss-Bonnet?
Um,
Because the Gauss-Bonnet thing says that the
Yeah.
interior saddle curvature can be written as
Yes.
an edge integral.
Yes,
And I wondered if it was that.
it is that.
Okay.
We, just to check it, we did it both ways, but yes, absolutely.
Could you please explain again why they don't form a closed shape like lipid membrane bilayer membranes? Is it dependent on the shape, size of the rods at all?
Yes, so if you have a membrane that has a resistance to bending and also a line energy cost, as the membrane wraps up to form a sphere, the edge gets smaller and so if the membrane is very large, so the point is that when the membrane is in a sphere, the bending energy doesn't depend on the size of the membrane. So let's just say that. So if we compare the energy of a closed sphere with a flat disk, as you make the disk bigger and bigger, the energy of the disk is going to get bigger and bigger because the circumference is getting bigger and bigger. So we'd expect, maybe there is a barrier, but we'd expect eventually that a membrane would wrap up and form. Okay, that's the expectation. We know what by measuring the fluctuations, we know what the line tension is. We know how big the membranes can get before they wrap up and form a vesicle. So we have a lower bound on the bending stiffness, and it's much bigger than 150 kBT, much bigger. With the FD viruses that I was talking about here. More recently, it's not published, they've been using shorter FD viruses, which you would expect would make a more flexible membrane. And they have huge ones, and they've gotten them to kind of wrap up and form a vesicle. So it's really, and we're also looking at that process. But it just seems that for some reason that we don't quite understand, if you go back to this Helfrich argument, it's what you would think for a plate. If you know what the Young's modulus is for the membrane, you know the thickness, you should be able to calculate the bending stiffness, and that there's just some confusion there, and that is, it's getting straightened out, but it seems that it's much larger than kappa bar.
Can you remind me, with that calculation with the plate and the
Yeah.
perimeter, if you increase the line tension at fixed size, there's a barrier, but does it eventually goes away altogether?
It does eventually
the
go away.
spinodal, so your bound
Yes.
comes from the spinodal point. Because I mean, if it's hundreds of kT for kappa, the barrier is still big while it's there,
Right.
but eventually there's no barrier at all, and it really just folds.
Yes,
Yeah.
that's correct.
Maybe following on some of the questions here, do I correctly understand that in this final stage of this time development series you had, these nice photographs, that some ripping has taken part, correct?
Well,
Or not?
not in that picture. They
I'm talking about the last one.
yeah, they
Maybe not.
I don't know. I don't know, actually detaching, they see all kinds of stuff, right? So this is a very nice example.
Can you say this is a typical sequence?
I think it's a typical sequence for a membrane, yes. And the detaching, we'd have to ask Svanimir about that. I don't want to say. Not that I know of, but.
And your hope is to understand maybe the scale of these ripples and how.
Yeah, so this is something, this scale is
Yeah.
comparable to this twist penetration depth, so this is precisely where this theory I've been using doesn't work. That hasn't stopped us from trying, and we've been analyzing just to see again how far we can get. So they can do things. They can take up here in the stable where the flat disk is stable. They can grab onto it with laser tweezers and pull onto it, and eventually, first it kind of deforms like a lens, and then it'll twist. It'll wrap up, and we've been able to see that out of or actually my student Leroy Gio was able to see that happening, but we're a little bit sidetracked now because, as I mentioned, here we shouldn't expect to use this effective theory, so we're looking at a simple problem where we put both in, like an axisymmetric problem. Understand that first, and then we'll come back to that.
Any more questions? Oh, that one. All this is in water, right?
Yes.
What happens when it dries? I'm sure the experimentalist has seen that.
I don't. It's a good question for the experimentalist. Since I don't do the experiments, it's not a natural question for me, but sure. Don't know.
Probably interesting.
Probably interesting, yes.
Okay, on this, let's thank Tom once more. Invite you tomorrow, for those of you who came late, tomorrow we have a talk at 3 right here, and then the reception at 4.